Okay, this is a video, another video about differential equations, and this is about growth and decay. So we have done separating variables, so solving differential equations and slope fields, and now we're going to talk about a specific type of differential equation dealing with growth and decay. So you should have worked with this previously, and definitely in a science class, possibly in chemistry and things, you may have worked with it. But we're going to review some of that stuff and then talk about some new things. Now, I may go through some of these examples very quickly, so remember this is a video, so you can pause it and catch up, or you can rewind it and go back if you're not able to keep up. So basically this original statement is what's leading us through this. So if they tell you that the rate of change of some quantity y is directly proportional to y. So the rate of change, that's the derivative, is directly proportional to y. And remember, that means it's some constant times y, or ky. So we've done direct proportion before. It's just this time it's a derivative that's directly proportional to something. Well, if that's true, if we've got a function, and in that function we know that the derivative is directly proportional to y, then we know that this will be the solution to the differential equation, where c is the initial value of y, and k is what we call the proportionality constant, or the constant of proportionality. If k is positive, then we have exponential growth. If k is negative, then we have exponential decay. So we'll deal with both of those. All right, so first let's prove that in fact that is actually what we get for the solution. So we're going to solve this using the methods that we just learned about previously. So I'm going to rewrite it over here so I can keep my work over to the side here. So remember, to solve this differential equation, we would want to separate the variables. Well, k is a constant, so I'm going to leave it on the right by itself and move the dt with it. And then the y needs to come over here with the dy, which means it needs to divide. And then we're going to solve from there. So we need to integrate both sides. Remember, after we've separated the variables, we want to integrate both sides. So the integral of dy over y is going to be ln of the absolute value of y. And it's going to equal kt, because it's a constant, plus c. Now we're going to go ahead and use our rules for exponents that say that when you have, for example, y equals log base b of x, this is the exact same thing as b to the y equals x. So in our case, we have ln of x, and remember that is the same thing as log base b of x, or log base e, sorry, of x. So in order to translate ln of y equals kt plus c, we're going to get the base, which is e, raised to the answer, the base raised to the answer, so e to the kt plus c is going to equal the inside, which is y. Now we have absolute value of y, but we'll see that we don't really need to do that. So again, absolute value of y is going to equal e to the kt plus c. So we don't need the absolute value here because e raised to a power is always going to be positive. So we can just write e to the y equals e to the kt plus c. Now we need to keep in mind that we're trying to solve this and get it to match something. So we need to use some more properties. So there were some properties of logs. Now here's a property of exponents. So if I have x squared times x to the fifth, remember that we would add those exponents and get x to the seventh. Well, we can certainly go this direction too. It's equal. So over here on our problem, we have e raised to the power where we're adding the powers. So we can make the base go to each one and make it a product. So all I'm doing is doing that property kind of backwards. Well, the key here is e to the c is e, which is 2.7 whatever, it's a number, raised to a constant. So it's still a constant. So therefore we can just simply write this as y equals a big constant e to the kt. And that's exactly what we just found out. So that's exactly what we were trying to show. Okay, so now let's use that in order to solve things. So it says the rate of change of y is proportional to y. So that means that we are saying that dy dt equals some constant times y. That's what it's saying. Well, we just learned that that implies that the solution is y equals c e to the kt. So we can just use that directly to solve this problem. So they've given us some conditions there, because what are the things that we don't know in this solution? Well, we don't know what c is, and we don't know what k is. Well, they've given us two different conditions, sets of conditions, and that will allow us to find the two things that are unknown. After we find c and k, we'll write our model down, and then we'll use that to answer this question. Okay, so they have to give us initial conditions to solve that. So first thing we're going to notice, very first thing to notice is that y does equal c e to the kt. And remember that you were told that c is the initial value, so that means y will equal the initial value when t equals 0, y is 3. So that means c is 3. Now you can plug in 0 and figure that out. If you plug in 0 for t right here, you're just going to get e to the 0, which is 1. So that's why that's the solution. So that's the first step. But I'm still missing, I still don't know the value of k. So now I'm going to use the second set of conditions to figure out what k is. So y is 6 when t is 2. So all I did was fill in. For y is 6, I filled in t is 2. So now I'm going to solve this. So I need to divide both sides by 3 so that I get 2 equals e to the kt. Oh. And then I want to solve this. So same kind of thing that we just did with the properties of logs, only we're going to go the other direction. So if we have e to the something is 2, that is exactly the same statement as ln of 2 equals 2k. The answer to a log is the exponent, if that helps you get that in the right spot. So once I know that, I can solve for k by simply dividing by 2. So ln of 2 divided by 2, put that in the calculator, and you're going to get about 0.3466. So we are now at the point, if I put those things together, so putting this together, that now gives me my third step, which says, okay, so I've now found out what c is, I now found out what k is, so therefore the model for this problem is y equals 3, because I found out what c is, e to the k, which I just found, which was 0.3466 times t. So this is now the model that I have for this situation. Then I want to figure out, okay, so now I can go ahead and do the starred part, which is actually solve. So I had to use all the conditions in order to get my exact model for this situation. And now I just simply find out what happens when t is 3. So we get y equals 3e to the 0.3466 times 3. And we get that y is about 8.48595, something like that. Try it in your calculator, and that's our solution. Okay, so let's go to the next example. So the next example is about bacteria growing at a rate of 3,000 e to the 2t over 5 per unit of time t. At t equals 0, the number of bacteria present was 7,500, so there's your initial condition. Find the number present when t is 5. So, the number of bacteria, so we'll just use capital B for bacteria, in a culture is growing at a rate. So that means dB dt, the rate of change, is 3,000 e to the 2t over 5. So that's what that statement means. Then we want to integrate both sides in order to solve this. And then we're going to kind of see that we could get to this answer a little bit quicker. But let's go ahead and go through this. So the integral of dB dt, which would of course be b, or we want to split our variables up. Sorry, I guess before we do that, we better separate. So we have just dB on this side, an integral of 3,000 e to the 2t over 5 dt over there. So we better separate our variables. Then we get just b. So b is going to equal the integral when you do this integration. So remember, leave the constant alone. E, when you integrate it or take the derivative, you just get the same thing. If I were doing a derivative, I would multiply by the 2/5, the derivative of the inside. Since I am integrating, I'm going to divide by 2/5, which is times 5/2. If I simplify that, I get 7,500 e to the 2t over 5. Well, we kind of know that because we know that the solution to that differential equation is c e to the kt. So we've now figured out that c is 7,500, which we kind of knew because they told us at the initial condition that we had that. So my actual function, b of time, bacteria and time, is 7,500 e to the 2t over 5. So now I want to find the number of bacteria present when t is 5. So that means I need to find b of 5. So that's 7,500 e to the 2 times 5 over 5, which is e squared. Put that in the calculator, and you're going to get about 55,418. You can round to the nearest bacteria there. Okay, so that's the next example. So let's go to another one. This is example 4. So we have another situation where we have some information given. They're telling you that there's an exponential pattern of decline. So this is exponential decay. So the situation is they've given us 2 different conditions again. And they told us that in 2008, we had $530,000, and that in 2010 we had $386,000. So there's basically your 2 initial sets of initial conditions. They're telling us there's an exponential pattern of decline, and then we want to answer for a later situation. So we know that the model that we need here is going to be y equals c e to the kt, because they told us it was exponential pattern of decline. Now we're going to solve for k and for t again, or solve for k and for c, but c we know because of the initial condition, and then we're going to solve for k, and then once we have that, then we plug in for the other. So some things to make a note of. So we're going to note that when t equals 0, that's going to be the year 2008. So we want to remember, when we use dates, we hardly ever use 2008 for the time. We would call that time 0. So therefore, t equals 2 is going to correspond to 2010. And so we'll end up using t equals 5 to find our answer, which is what is going to happen in, or what we predict for 2013. So what that means is the information that we know is one ordered pair is time 0. We have 530,000. And then we also know at time 2, our revenue is 386,000. So those are our two conditions that we know. So let's use those conditions. So first, we know that C is always our initial condition. Well, our initial value is 530,000. So we have this much part of the model. Now we're going to use the other information to plug in. So we know that we have when Y is 386,000, or Y is going to be that when T equals 2. And so now we would solve this. So we want to solve this one for K also. So we're going to solve by dividing both sides by 530,000. So we're going to get 386 over 530 as a quick divide here, e to the 2k. Then do your ln again. So ln of 386 over 530 is going to equal 2k. So that means that k must be ln of 386 over 500 or 530 all over 2. And then let's get a decimal for that because we really want to have a approximate number here is good enough. That's negative 0.15852. Now, are we okay with negative? We should be because it says it is declining. So we know that K would be negative because we have decay. So putting all of that information together means that Y will equal 530,000 because that's C, E to the K, which we just found was negative 0.15852 times T. So this is now the model. We used our conditions, we filled in the model. Now we want to know what happens when we have 5. And so we want to know what is Y of 5. So that's 530,000 e to the minus 0.15852 times 5. Put that in the calculator and we get approximately $239,913.16 expected in 2013. Okay, so there's an example with decline. All right, so let's talk about another example that increases or decreases, and the difference here is we do not know the initial value. So we know that we have a population of insects. It increases with exponential growth. Okay, so that's an important part to underline. We know that after the 3rd day that we had 130 insects, and we know on the 7th day we have 380 insects. So basically we have 2 ordered pairs there. 3rd day 130, 7th day 380. So the difference is in this example we do not know the initial. So what we're asked for here is actually the initial. But we do know, first thing we know is the model that's going to fit is going to be Y equals C e to the KT because it said it is exponential growth. And then what we're going to have to do to solve for C here is we're going to have to set up 2 equations using both of those ordered pairs and substitute one into the other. So you're going to have 130 equals C e to the 3K, and you're going to have 380 equals C e to the 7K. So all I did was substitute those 2 ordered pairs. Now what I can do is solve one of them for C and plug it into the other one. Okay, so now my process would be, so second thing was get some equations going here. So third thing is take one of the equations, so I'll just take this first one, and I'm going to solve it for C. So this would be C equals 130 over e to the 3K. Well, we can write that easier as 130 times e to the minus 3K. Remember, when you move an exponent up from the bottom or other direction, whichever direction, it changes signs. Now we're going to take that and we're going to plug it into the other equation that I have right here. So we know that we're going to get 380 equals And instead of c, I'm going to write what I just found, which is 130 e to the minus 3k, and then that's going to be times e to the 7k. So basically what I have written in black there is just the substitution. So now I can just do some solving. So 380 equals 130, and then remember, when you multiply with exponents, you add the exponents. So that's going to be e to the 4k. And now we solve it like we've been solving it. So 380 over 130 is going to equal e to the 4k. So ln of, I'll write 38 over 13 because I can cross the zeros off, equals 4k. So therefore k equals 1/4 of ln of 38 over 13, which is approximately 0.268159. Now the difference is that's, now I found k, but I don't actually know c. So I want to actually find that at time 0. So I'm going to take that information and I'm going to plug it back in to our model. So now I have that k is 0.268159 times time. But I want to find out what is happening. I want to find c out. So I got to take one of my initial conditions. So I had either 3, 130 or 7, 380, and I'm going to plug that in, and that will leave me only the c that I don't know, because if I plug in for t and I plug in for y, then I can find c. So that's going to give me 130 equals c e to the k, write all that down, times time, which is 3. So when I go through this process, I'm going to get c as 130 over that e to the stuff. And that's going to give me that c is approximately 58. So we have about 58 insects initially. Okay, so we have 2 more examples we're going to go through, and we're going to go through these pretty quickly. We're not going to do a lot with half-life, so we just want to kind of mention it though. So the model for half-life, we kind of figured that out in a lesson earlier, is that when you have half-life, the final amount, so the amount final, is equal to the initial amount times 1/2, and then you raise it to the time divided by k, where k is the half-life time. So we kind of did a problem and noticed that this would be the formula. So we can skip to that when you have half-life. So this is what you're going to use for this problem to solve it. So all we're going to do is fill stuff in. So the final amount, we want to know how long does it take to get to 125. So 125 is the final. The initial amount is 4,000. And then it's 1/2 to the t over, they tell us it's 700 million years to decay for a half-life. So we'll put 700, so our answer's in millions of years. So all we have to do is solve this. So we take and divide by 4,000. And then we're going to solve that by taking the natural log of both sides. So this is how you solve exponentials. So you need to pull back in the memories of that. We're going to take the natural log of both sides. The reason that method is very helpful is because logs have that awesome property that you can, so this side we're going to leave alone, but you can do the awesome, you have the awesome property that you can take your exponent, remember, and pull it in front. So that's why taking logs is helpful. So we have t over 200 times ln of 1/2. And so if I want to solve for t, I'm going to simply want to think of this as a fraction. This is the numerator, this is the denominator, it's over 200. So if I want to get t by itself, I want to flip and multiply by that. So I'm going to multiply by ln of 1/2 over 200 to get that by itself. since we want to use the calculator for this, that's why I'm not bothering to simplify very many things, because you're just going to type it all in the calculator. So if you type it into the calculator, oh, I wrote t over 200 instead of 700. Just realized that. So this was t over 700, not 200. So that's a 7. So we're going to need a 700 there. And then we just put all that in the calculator and find out that t is going to equal 3,500. And then remember that was in millions of years, because we just used 700 for million. So in million years is when you will find out that the radioactive element will decay to 125 atoms. All right, last question. Again, remember, you can rewind, stop, pause, everything. So I'm going to go through this quickly. You can pause and read the question. So Napier invented logarithms, or he's credited with it. He also answered a lot of questions about monetary growth. So this fits perfect. So if money compounds at a rate proportional to the amount you now have, so let's translate that. So we'll call capital M to be our money. So if the rate of change of your money over time is directly proportional to the money that you have. So that's basically translating that statement. The change in your money over time is directly proportional to the amount of money you have. So that's Km. Well, that's the differential equation we've been dealing with. Instead of using y and c, let's use, like we did with the half-life, your final amount of money equals your initial money, e to the kt. And you might remember this when you did Algebra 2, you probably did PERT, that a equals pe to the rt. It's basically the same concept, and we're just developing it from the calculus perspective. All right, so now we want to figure out what K is. Well, what we're going to do to figure out K is use the information that if you're investing at 5% interest, we want to know how long does it take $100 to grow to 1,000. Well, investing at 5% means that, let's say that my initial amount of money, so let's go over here. If my initial amount of money is $1, let's say, e to the k times 1 year, so we're going to say in 1 year I'm going to have $1.05. We can use any amount of money. It doesn't matter. I could use $1,000, $1 million. In 1 year, if I'm getting 5% simple interest, I'm going to have 5% of that money plus the initial amount. It's easiest to think of something like $1. If I have $1, I get 5% interest. In 1 year, I have $1.05. So that means if I solve this, that ln of 1.05 is going to equal k, using the same exponential changes that we've been doing. So therefore, I've now found what k is. So my model is the monetary money, the money final equals the initial money, e to the ln of 1.05 t. So that's what my k is. Ln of 1.05, and you can get a decimal for that. So now we just take the information that we have. We want to know how long does it take us to take $100 and get $1,000. So that's e to the whatever ln of 1.05 is times t. So if I solve that, I'm going to end up with, if I divide by 100, I'm going to get 10 equals e to the ln of 1.05 t. And if I write the exponential that goes with that, I'm going to get ln of 10 equals ln of 1.05 t. So divide by ln of 1.05, we get ln of 10 over ln of 1.05 is going to equal t. So t is going to be about 48 years. You can round that pretty liberally because we're just giving that as a big amount of time. All right, so here are a bunch of examples of that, but that's definitely on the AP test. Very helpful to know how to solve that type of problem from just knowing that it's exponential.